Alright, hello everyone, April 27th. Alright, let's do this. Bulb switcher. And after that, I said I'm going to learn the new method, but I actually thought about something. I think I might be able to do this without DSU. Maybe. We'll give it a shot. Alright, bulb switcher. There are N bulbs that are initially, oh my gosh, so many people hate this question. Initially or off. You first turn on all the bulbs. Then you turn off every second bulb. On the third, you toggle every third bulb. So the second round is toggle every second. For the ith round, you toggle every ith bulb. For the nth round, you only toggle the last bulb. Return the number of bulbs that are on after n rounds. Are we doing like, this feels like a week of what? Modulo. First is 3, and then this is off, and then this is off, so we have 1. Useless. Yeah, this is 100% mathematic. So I don't know. I mean, we can give it a shot. Like, so we can say 1, 1, 1, 1, 1. I don't know. This is how many? 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? We have 9. N equals 9. Right? So the first time is all the this is round 1, so round 2, and I think it starts from 1, so it'll be 1 0 1 0 1 0 1 0 1, right? And then round 3 is everything divisible by 3, so 1 2 3, the third one, right? So 1 0 0, okay? Don't change this one, and then it'll be this. So what is it like? It's like, it's like every value, every number, right? Like how many times it will hit, okay? And the first one will never be hit, right? Because it has to be 2k, right? We can say 2k, and then 3k, and then 4k, all the way to n. I shouldn't say k. I can say I can say k2, k3, k4 to nk1. Right? All of these is just things that will hit. And the first one will never get hit. So first one will always become 1, unless n equals to 0, right? So first will always become 1. And then now look at 2, right? For 2. 2 can only be 2 times 1. Can it be 3 times something? No, they cannot. So the 2 will always become 0, no matter what. Now you look at 3, right? 3 equals 3 times 1, and what? Can it equal to 4 times something? No, they cannot. So 3 will always become this, right? Now 4. 4 will turn off because 4 equals 2 times 2, and 4 equals 4 times 1, right? So this will turn into 0. This is actually turn on, and that's it. So the fourth one will always be on. Now we cannot just go analyze everything, so we need to summarize the so what are we looking at? Let's say 5. So 5 is a prime, so prime will always be 0, and that's it, because there's no other way, right? So prime will always be 0. 6. Okay, so every value, every value will be able to, like say 6. What's 6? So 6, we hit a 2, we hit a 3, 4 cannot, 5 cannot, now we hit a 6, right? So we hit a 3 times. So 6 will remain on, right? 6 will remain on. Are we going to analyze everything? I don't think we should analyze everything. But hold a second. How about 8? Like 7 is just always off. How about 8? Okay. 8, we can do 2, 4. Oh, that's it. And then 8 times 1, right? 5, 6, right? That's it. How about 9? 9 we can do 3, 4, 5, 6, 7, 8, 9. Huh. What is the pattern? Alright, so this will toggle off and then toggle on. Alright, toggle off, toggle on, toggle off. So basically, we want to know how many, for each given value, how many times it can be, it's always going to be odd number. If you think about it, right? Whatever value, let me use let's say 24, right? So we can say 2 times 12, 3 times 4, no, 3 times 8, 4 times 6, right? So whatever you do, and then once you cross the halfway line, you always go, right? 8 times 3, 12 times 2. And actually you can do 1 times 24 as well, right? 1 times 24. And then at the end you do 24 times 1. So it will always be symmetrical, which means it will be on, off, on, off, on, off, on, off. So it will always be off. We'll have the same amount of time to turn it on and the same amount of time to turn it off. So everything shall be off. Like these are all off because 1 times 6, right, is on, off, on, off. So the only thing that's not the case is the 1, right? Is the 1. 25, right? We have a 1 times 25, 5 times 20, 5 times 5, and 25 times 1. So if you are a square value, right? If you're a square value, then you will be always on. If you're not a square value, you will be always off. So what I'm saying is 1 will always be on because 1 is 1 squared, right? 2 will always be off, 3 will always be off, 4 will always be on, right? So it turns into a problem, and then 0 is a special case. It turns into a case of given n, right? Right, we say given n, how many square numbers are smaller or equal to n. Can we do that? Yes, we can, because if you give me n, I can always, because we are asking, right? What we're asking is, like we're given the x, I want x squared smaller than n, smaller or equal to n, right? So x is smaller or equal to square root n. So we get square root n. Actually, we get not really square root n. What we get is the floor, right, of square root n. We get the floor of square root n. That is how many values that are square numbers that's smaller or equal to n. So the answer shall just be this. The result shall just be this. And it fits 0 as well, right? Okay, so this is how we are going to try. Wait, I mean, I know why people don't like it, because they're always like, oh, this is, supposed to be programming, coding, and it now turns into a mathematics. And I was just like, come on, this is not really, it is not programming per se, but it is also just some, I think I probably don't need math.sqrt. I'm not sure. Does math has sqrt, or we can do sqrt directly? I think we do need. Oh Jesus, why you have an R here? Yeah, you see 10 to the 9th, most likely it's going to be mathematics. Is it invalid? Well, we have something that's too big. Jesus, man. Way too big. 1, 2, 3, 4, 5, 6, 7. Okay, 7 should be fine. Yep, I think that's the case. Oh, I've done it before. What was my initial solution? I was really trying? That's 28 milliseconds. That's 540. Oh my goodness. What was I doing? I was sieving it. No way. I have no clue what I was doing back then. Nah, I cannot figure this one out again. I'd rather not look into it. This is the, yeah. Uh-huh. Any non-square number has even number of factors. Yeah. I don't want to say it's even number of factors, but we can break it down. Yep. Does that mean you have improved? I think so, man. I think this means I have improved. Improved from 2021. So I like this problem. I think I have improved, right? Because I am able to arrive at the good solution by myself. The last time I did this problem was December 2021, and at that time I was not able to figure out the trick that the solution, right? The solution is the number of squared numbers smaller or equal to n. Now the intuition is this: given any num, right, we can write it as num equals 1 times num. Let's just say a1 times b1 num equal to a2 times b2 and then num equals a k times bk, right? And then num equal to bk times ak, and num equal to, and then right, num equal to b2 times a2, and num equal to b1 times a1, in which in these breaking downs, a1 smaller than a2, smaller smaller to ak, right, and then smaller than bk minus 1, right, smaller than smaller to b2, smaller to b1. Therefore, any non-square number always have even number of ways to break it down, which means they have even number of toggles. The result, right, is that any non-square number will always remain turned off after all the rounds. Thus, we only need to find the number of squared numbers within n. That can be achieved by math.floor, math.sqrt, and yeah, I think this will be called a login. Okay, so this one is done. I want to try this one more time. Obsession, man. There's a certain thing called obsession. Okay, let's go back to our... Okay, go back here. Let's do the obsession. So, all right, we have this. 1, 2, 3. 1, 2, 3. Okay, so we have 4, 0, 2, 0, 3, 0, 1, 2, 0, and 1. So the idea is exactly the same. We will find all the positions that are the same, and then we'll assign value to them. Now, we can start the result, right? The result, we can always start with A, and then something, 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 right? And we go from right to left. Okay, so we'll check 0, 1, 2, 3, check with 3, right? Which is totally fine. If they are the same, and then 0 has been set, then we set 3 to A. If they're not the same, then we don't set 3. Then we check 2, right? We check 2, 3. If this is larger than 0, then we do. So basically, A, we know that this is the starting position. And the first row, we can fill everything that is equal to A. In this case, 2 is equal to A, so we fit this is A. And these are not equal. So after done, which means we have already filled everything that's equal to A. So when we go to the second one, I plus equal 1, so we go to this position, right? And then A is already used. So this one has to be different, so we set this one to B. And then we do exactly the same thing. We go from back to front. And now the back is good. So boom, we filled it, right? We filled it. And then we just keep going, right? If it's not filled, then we just do it. And in fact, by doing this, we might be able to identify the error immediately, because every row we're filling new ones. Every row we're filling new ones. If there is something that's wrong, and we can know immediately, this might actually be a better solution. And I'm pretty confident that this is the solution from Lead 215 or all those people. Okay, so solution 2. Okay, solution 2. So this is a same idea as solution 1, but without using union find. For each row of LCP, right? For LCP I, right? We can, if we go from right to left. Actually, it doesn't matter go from right to left or left to right. Right? If we go for each this, we can identify all the positions in the result that share the same letter as res I, right? Then as we go through LCP row by row, we will fill out res and at the same time check, right? Check whether the already filled positions match the future requirements. Okay, so we will do this. Okay, res is equal to this times n. Okay. Then we say for I in range letter is equals 97 in range n. Okay. And then we'll always say if res I, if not res I, which means it's empty, then res I shall equal to character letter. Okay, we're going to say if not, if letter is larger than 122, right? Is it 122? Yeah. If this, then we shall return this. It's an impossible case because we go beyond z. Otherwise, we'll do this, let plus equal 1. Okay. Now we can say for j in range I plus 1 to n. So everything, if we can say if LCP ij, okay, then we say if res j, if not res j, then res j shall equal to res I. If res j is not equal to res I, I will return this. Right, they should be the same, but they're not. Right? They should be the same. It should be the same. And then we go to the end. Then we go back, I increment, and we try to fill, and this should be right. And if we fill this entire thing, we still need to check. We still need to check this, unfortunately. We still need to check. Right, we still need to check. So this is the fill, okay? Say fill, find the smallest string that satisfies LCP, and then check if it's good. I mean, we can check here. We can check. How do you propose to check? Well, there are stuff that we can check at this point. We can check diagonal. We can check, but how do you propose to check? If we go from I, right? But the value, you have to check the value. So yeah, let's do the check by itself. Wait, check is here, and then the fill-in will be here. But in the fill-in, we can probably end it early, right? End it early. I mean, we can do some check here. We can say if LCP ij is not equal to LCP ji, right? Then we just return this. So this is check mirroring. You say find the smallest. Also, we conduct some validation. So we have this validation. I mean, we can also validate if it's too big, right? How do you validate that? So we can say if LCP ij right, is larger than n minus j. Is that right? At a 0 position, oh, j will never be 0. So at a 1 position, the largest is 3, right? Because we can have 3's matching. So from the last position is n minus 1. N minus 1 minus j plus 1. So n minus j is the largest. So if it's larger than this, right, value too large, return. So these are the check we can do. And what else will check we can do? Yeah, the thing is, like, if we do the check here, we might be able to exit earlier, right? We don't have to go through the whole thing. What else check we can do? I mean, we can do the diagonal check if you want to check the diagonal. Nah, I kind of don't want to check the diagonal though. You don't want to check the diagonal. We can check the diagonal here, right? We can say if LCP II is not equal to n minus I, right? So the start, yeah, if it's not equal to this, then we return this. So check diagonal. There's one more check we can do, right? We can say if I is larger than 0, okay, and LCP I minus 1, j minus 1, and LCP I j is not equal to LCP I minus 1, j minus 1, minus 1. Return this. Right, this is check diagonal. Other diagonals. So we have 3 check. Actually, 4th check, we have this as well. So we go through all of this. If they all good, then we do one more check here, and then we return the result. Let's see if this one works. Okay, it works, but I think it's actually, do you feel it's slower than this? 80. 74. I guess it doesn't really matter too much. I'll put it here. Okay, and I want the timeout to see if this one will work for the timeout. See if it works. Ooh, that was slow. I mean, it definitely works. We just, if, I don't know. What do you think? I think you might save some small time, but by having all these if-else, I think it might actually slow things down. Okay, what if we don't do this? I mean, we can definitely, this we have to check. This is something that we cannot check by doing this. We have to check here. So we do this. Mirroring we'll check later. All these we check later. And all we do is, this we can check. We can check at the moment. Right, so it's like just a small check. So 1802. How about this? How fast does this one go? I think it's faster, huh? Try it. Oh yeah. Oh yeah. Look at that. I don't know the last time I scored 99%. Look at that. Absolutely. Absolutely. Yeah. And it's clearer, right? It's open squared. And it's faster. Oh, it's so much faster. I think this is the good solution. Yeah, because we don't have to use union find. Union find still takes time. This is just O(n) squared here. O(n) squared here. And that's it. Done. Good. Good. Okay. That's good. Now we can turn this off. Alright. We spent so much time on that one. Oh, now we have so many pages we haven't done. Oh, God. Okay, let's do at least one more. Left and right sum difference. What's that? Zero indexed array. Find a zero indexed integer array. Answer where answer the length. Answer I equals left sum minus right sum. Left sum is the sum of elements to the left of the index I in the array. If there's no such element, it's 0. Right is, so it's the prefix sum or suffix sum, right? So, okay, let's go here. I just open a new page. Okay, so what do we have? We have 10, 4, 8, and 3. So the left sum, if I understand it right, is going to be 10, 14, 22, and 25, right? And the right sum is going to be, actually, 3, 11, 15, and 25. So the answer shall be the absolute difference between the two. So it will be 15, 1, 11, and 22. Yep, that is correct. Okay. So num is 1000. So we can definitely just do it, brute force. But do we have a better solution? I don't know. So we have 10, 10 plus 4, right? 10 plus 4 plus 8, 10 plus 4 plus 8 plus 3. And now I have 3, 8 plus 3, 4 plus 8 plus 3, and 10 plus 4 plus 8 plus 3, right? So I want to find the difference between them. I don't know, is there a better solution? I don't think so. Maybe there is, but I don't see it. I mean, we can say the difference between these two, right? The difference between these two is this, right? But the difference between these two are not this. We do cancel out this, but now we have a -3. And the difference between these two will cancel this, but now we have a 10, I have an 8-3. So you know what? Let's just do it the stupid way, because it's, I don't know, maybe the hint will give us something. I mean, no matter what, the runtime is always going to be O(n), okay? And we have from iter tools, we have something called accumulate. So we can always say left sum equals list accumulate. Yeah, list accumulate nums. And then right rs will equal to oh, we're gonna fill from right to left. That's fine. Rs equal to nums minus 1. Okay. Result equal to this 0 times len nums. Okay, I range len nums -1 -1 -1. All right. Actually, let's do this with 0. rs plus equal to nums I, and then res I equal to left sum I minus rs, and we do abs, and then we return res. Yeah, I think that shall be it, unless there are other better solutions. Yeah, a couple of weird test cases. Yeah, I shall be right. Yeah, nothing too special, right? What are the hints? Yeah. Okay, so that's that. I'll do another one. Okay. Find the divisibility array of I was gonna say a string. You're given a 0-indexed string word of length n consisting of digits and a positive integer n. The divisibility array div of word is an integer array of length n such that div I equals 1 if the numeric value of 0 to I is divisible by m. 0 if it's not. Return the divisibility array. So we have 998 and by 3. There are only 4 prefixes that are divisible by 3. 9, 99, 998 is bad, 998, 984, 984, 99244, 9924, 998244. Can we just do it? Left to right? Yeah, I think that's fine. I don't see why we cannot do this, right? I think we can just go straight ahead. Nothing too tricky. Right, we can say val equals 0, right? And then for d in word, now we have a result equal to this. Val equals to val times 10 plus int d, right? And then res dot append val mod m. Hold on. Equal to 0, right? And then we have to int this thing, and then we return res. Like, what would stop this from being right? Is that right? Yeah? I don't see any trick in this. Oh, was it be slow? Oh, it's going to be slow. Didn't realize that. I mean, we're doing this so we can mod along the way. Right, we can mod along the way. And dear Lord. Ah, that's how you accumulate the error. Yep. Yeah, I didn't realize that. Didn't realize that was my bad. Too fast. I didn't realize how much The constraint. Is that 10 to the 9th? That's the constraint is 10 to the 9th, right? N is 10 to the 5th. So the value is 10 to the 5th. I guess if we mod, that's just too big. Yeah. One trick, right? It's a one trick. One trick. Keep modding modding the value converted from word. Otherwise, we will TLE. Okay, so that's that. I guess that's the only trick. With image, track mod. Yeah. Holy crap. This is already mod. Damn it. No need to mod val again. Yeah, it is already the mod of M. Darn it. It's alright, but we already computed it, so you don't have to compute again. Okay, so this is done. Next, yeah, we like mow through them pretty fast. Find the maximum number of marked indices. You're given a zero-indexed integer array. Initially, all of the indices are unmarked. You are allowed to make this operation any number of times. Pick two different unmarked indices such that 2 times the first one is smaller than the second one, then mark ing, return the maximum possible number of marked indices in nums using the above operations any number of times. So, okay, you have 3, 5, 2, 4. In the first operation, pick I equals 2 and j equals 1. As long as 2 times the first one, this operation is allowed. 0, 1, 2. 2 times 2 is 4. This is allowed. So return the maximum possible number of marked indices. So we want to mark as much as possible. You can be sure that there's no other valid operation to mark if it's smaller or equal to. So first one, so the I pick, so double that has to be smaller than the second one. So double that. The second example with double 4, smaller than 9, and then with double 2, it's smaller than 5. Okay, so first things first, we sort them. No question about it, we sort them. Right? So in the first case, I can say, because it doesn't really matter, I and j, there's nothing. So we can sort 2, 3, 4, 5, right? The first one. So what we want is the smaller one, right? And then we need a times 2, right? So we have 4. Anything, so with the smaller one, so 2 times 2 equals 4. So we want to know among these, what is the smallest value that's larger equal to 4. And it's 4, so we'll mark these two, right? Next one is 3. And 3, it's on the outside. Then we're done. Which means what we can do is go from this, right? Go from this, and we will binary search. Well, we can binary search, bisect, find it, mark it, right? And mark it. And then the next one, we can do this, so we can mark. And then when we mark, we can probably just put that into a set, right? We put this into a set, so this is marked. And next one, what if we had duplicates, right? Duplicates. That's fine. We use a counter. Okay, use a counter, so we have a count. So if duplicates, we can just reduce the number. And oh, that's actually better than duplicates. When it becomes 0, then we can just eliminate it from oh, hold on, eliminate it from this. I don't think that's a wise way to do, man. But anyway, so we go from this, that will hit everything, and then the next one must be something bigger, right? Next one must be something bigger. But what if we have a lot more 2s? Then we will get into the next ones, right? Let's see. I mean, to fit it, definitely we want to fit the smallest. So I see how many smallest do we have? Okay, and then we see we can binary search. We can binary search to find how many of this we have, and if we have enough. You know what? Maybe or better if we do this, let's say 2 pointers. Right? We have an I here and have a J here, right? So the I is the current smallest. I know how many there are. J is 2 times of that, which is the smallest so far. That's fitting. And then, while J can not cover, then J will move forward. Right? When you cover as much as we can. Once we cannot cover, J stay there. And then once it's covered, I move on forward. So I go to 3. But 2 times 3 is 6. And this should keep moving forward. So we keep doing this, right? We keep doing this. And what's the result? We want to find the maximum possible number of marked indices, right? Which means every time. So if I know the starting position of J, right, we can say Sj. Si is always going to be 0. Sj is whatever bisect, right? Whatever bisect give us. And then I will start with Si, J will start with Sj. And these will go. Once we end, right? Once we end. Oh, hold on. That shall be the total number of values, total number of numbers. Now, these are the indices of the key. They don't count. So once we move forward, we have to go all the counts, right? Ooh, dude. So we're always trying to fit this, right? So if this is big, we go. Whenever this moves forward, it's gonna be the count of this multiplied by 2. And then we try to fit this, right? And then we will get rid of some of this. And then, no, whatever we get rid of, we put into the result, right? If say this, if we have fall of 2, right? We'll have 2, 2, 2, 2, right? If we have fall of 2, and then we have, let's say, 2 of 4, then we know we'll do 2, so this becomes 2, but then the result will equal to 4. Yep, I think this shall work. Oh, it's not simple. It's going to be, this is a programming problem. This is a programming problem. All right, first things first, we need a counter, okay? From collections, import counter. Can we finish this? Before the timer hits 1 hour? Okay, so we counter, and then we have keys equal to sorted counter, rest equal to 0. Okay, and then we need from bisect import bisect what? Doesn't matter, right, left, it does not matter because index, so starting I is equal to 0. Okay, starting j shall equal to bisect right keys keys 0 times 2. Right, the smallest times 2. So this is sj. So if they are the same, actually I don't want bisect right. I think I want bisect left. So if it's fitting, that will be the starting position. Okay, so we have si and sj, right? That's the starting position. And we say while sj is smaller than len keys, right? Then we say what? We say while counter keys, no, si equal to I, sj equal to j. Okay, so this is going to be j, keys j. While this is smaller or equal to, no, if this is, so we can remove that. Okay, so be while counter keys j, and this is smaller or equal to counter keys I, right? If the j is smaller, then we'll say counter keys I minus equal to counter keys j, right? And then rest plus equal to 2 times counter keys j, and j will plus equal 1. So while j is smaller than len keys and counter j and this, right? So j move forward, right? And j move forward, if it's still smaller, equal to, then we remove. We'll remove everything, right? Then we'll move forward. Right, we move forward, and the counter keys I is constantly decreasing, right? Decreasing. So at a certain point, counters j is going to be larger than what counters I have, and that is when we jump out. Now when we jump out is going to be if, right? If, so j will always plus equal 1. So jump out, we can say if j is smaller than len keys, right? If j is smaller than len keys, if j is smaller than len keys, which means when this jump out is, we'll check this, but the reason is, do we need this then? I mean, initially, well, that's definitely be larger. Yeah, we don't need this because keys j, counter keys j will always be larger than 0, so we don't need this, right? So this will be 0, but we always plus equal 1, so they come out. If this, then we know counter keys j has more value than counter keys I. Then what do? We do counter we do counter keys j, right, minus equal to counter keys I, right? And then res plus equal to 2 times counter keys I, and then I plus equal 1. Then we go back to the top, right? Go back to the top. And then we make the comparison again. Now counter keys j minus this, if counter keys j becomes 0, because I plus equal 1, this will definitely be not 0, right? This will definitely not be 0. Yeah, this will definitely not be 0. So this will fulfill, and this will just minus 0. This will plus 0, which is fine. J plus equal 1. So, and then at the end, we just return res. I feel then we are not using s. We just do this. That should be fine. I'm not that confident with this one, so let's run the test cases. I mean, the logic seems sound. This is definitely like greedy, right? We're not really checking anything. This is just as greedy as it can be. This is what? Nums max nums. That's pretty bad. That is pretty bad, man. That is pretty bad. Ugh. Okay. Let's see, what do we have? Let's say print key, counter, keys, I and j. Counter is this, keys is this, I is this, j is this, 0 and 2. That is all correct. Okay, j is smaller than keys, and counter j is smaller than that, right? Oh, shoot. I forgot to do something. Oof. While, oh my god, so many while keys j is, no, keys I times 2 is smaller equal to, no, is larger than keys j, right? Then j plus equal 1. Well, j is small, alright. And let's do m equals len keys. Too many len keys. I'm tired of seeing this. Okay, so while j is smaller than m, and this, then j plus equal 1 plus equal 1 plus equal 1 until we fit something, then we do this. Then we do this, right? So what if this is larger than yeah, what if both are 0? We do this, j plus equal 1, and then this will be 0, so we don't do anything, which is fine. Okay, so this is right. Yep, forgot a very important part. Okay, so this looks promising. Okay. my way of doing. Try it. It's 1 hour now. Oh my god. Edge cases, man. Edge cases. Jeez. Oof. All right. It's not as good as I had expected, but we gotta figure out a better test case. We cannot use this. This is way too ugly. How about we use this? Okay, and let's get rid of half. Does it work? You gotta be kidding me, man. How about we limit the first half? Oh, you gotta be kidding me. So how about we take the middle? So what is it that make it wrong? Oh, no, 10 is still right. Gosh. All right, can we just peel off a few values? Because I feel this is just too big. This is funny. All right, this is just really funny. Oh, good. That's good. Can we peel off even more? No, we cannot peel off more. At least I peeled off this value. This is a huge sore in my eye. No, you have to keep that. Okay. Alright, it's not. What if we make it smaller? Oh, it has to be a big value. Doesn't matter. Okay, that is our thing. And is it too many? Yeah, I guess, but expected 14. Output 16. Alright, just take a look. Counter keys. Okay, so we start from 3. 1, 1, 3. 2 times 3 is 6, so we immediately go to 42, right? So 3 and 42, done. Oh, 3 plus equal. Oh my god. Oh my god. Yep, I know what was wrong. Dude. Okay, so yeah, so one might catch up, right? If it catch up, then this one's already used. So everything has to move to a position that has not been used before. Okay. It's fine. Okay, let's rethink. Let's rethink the whole thing. This is good, right? And we say if J, whatever they have, is smaller than what I has, right? Then we'll do this, then we'll move forward. Okay, so we shall say current equal to this, and then this minus this, and actually it's fine. We can say do result, and then say counter keys j equal to 0. I want to set it to 0 and j plus equal 1. Okay, Then we try it again, try it again, try it again, until we find something. Now we go to here. Okay. Well, j is smaller than so j is stopping at some position. Now we're looking at I. Okay. So I need to plus equal 1. Right? Then j is bigger. So I think this is fine, but we also need to set counter keys I, and you set it to 0. Then I plus equal 1. Okay. Now, for this, we shall say while this and this or counter keys j is equal to 0, then j need to go to the first one that's not equal to 0. And while I is, what if everybody is 0 and then they meet each other? I think I should go first. While I is smaller than m and counter keys I. Alright, counter keys I is equal to 0. If this is equal to 0, then I plus equal 1. Then while this, and if I is in front of j, then this will definitely, so j will keep going. So if we do this, this one will pass. Okay. Oh, there's a lot of weird things happening here. So many wild statements. Ah, Lord. Do we have the original? Okay, this is the original. Oh my God. Expected. Oh. Expected. Wait. You haven't tested this one. What? Dude. Answer is 4. Result is 2. Huh? 2, 4. Ooh, it does not work. Ho, ho, ho. Ho, ho, ho. Wow. It's, yeah, it's harder. Yeah, if you do greedy, 2 you find 4. Now we have 5. Now 5 and 9 doesn't work. Dude. Then what do we do? So why 2 need to find 5? All right, we'll think about this tomorrow. This is harder than I expected. Anyway.